All right, welcome back, everyone. We're going to look at a truncus today. Apologies for all the Desmos stuff. Well, I'm not really sorry about it. It's the best thing I can think of to use, but you might be getting a bit sick of it. So we're going to look at a truncus today. Now, I've started with a hyperbola because a truncus is related to a hyperbola. It's actually the next, I would call it an iteration of a hyperbola. It's exactly the same form, 1 over x, except the x has been squared. Now, let's see if we can work out what would happen here. So first of all, you've got your hyperbola. Now let's imagine that we take all of these y values and we square them. All right, so you might have a look at this one here, which is 4.25. So this is a quarter. What's a quarter squared? So a quarter times a quarter is going to be a 16th. So that's made it a bit smaller. Out here we're going to have the y value of 3. So 3 squared is 9. So that's going to make it a bit bigger. What about these ones on the left-hand side? You're going to have minus a half. And minus a half times minus a half is going to be positive a quarter. So it looks like this left-hand arm here is going to flip over and go up there. That's what it should go. All right, so let's just have another quick check. We've got another point here. Whoops, this one here. Minus 1 times minus 1 is just 1. So it's moved up to the positive side as well. Have a look at this one here. Minus 3 times minus 3 is 9. So it's moved up to the positive side also. So our assumption seems to be holding true. So let's just go ahead and turn on. Oops, I'll just bring that back. We'll turn on the truncus and see if our idea is held true. There's the truncus. Look, it's actually done what we expected it to. It's once the left-hand side has come up here, so it's pointing up. I'll call it pointing up. Hopefully you know what I mean. Minus 1, which this point here has moved from minus 1 to positive 1. Same x value, different y value. This point here has moved to, I don't know if you know what 0.111 is, but I recognize it as a ninth. So 1/3 has moved to 1/9, which we know as 1/3 squared times 1/3 times 1/3 is 1/9. So that works out. Let's have a look at the right-hand side. This one here, we'll have a half. A half times a half is now a quarter, which you can see it's moved down. This one here, which was 2, has now moved vertically upwards to a 4. So 2 times 2 is 4. This one over here, a quarter. A quarter times a quarter is now a 16th, and we'll just have to trust that 0.063 is the same as 1 over 16. And we can keep going if we want to, but we get the idea. So this purple graph is called a truncus, and it's called a truncus for the very simple reason that it looks like the tree trunk, basically. All right, so it has the same basic features as a hyperbola, which is that it has two asymptotes, one a vertical and one the horizontal, and that's about all you need to know at the moment. But you will notice that it's not in two diagonally opposite quadrants; it's in two quadrants that are next to each other to create that tree trunk shape. So scrolling down here, let's have a quick look. This is the basic form of a hyperbola. So you've got a over x minus h squared plus k. So again, we use the same h and k values as we have for quadratics and hyperbolas. We use the same dilation factor, which is a, and it's even in the same position as for a rectangular hyperbola. So going back to this, let's have a quick look at what happens when I change the dilation. Will anyone be surprised? Oops, I have to turn this one on. Will anyone be surprised to know that I'll just move this k value to 0, h value to 0. The dilation factor does the same thing as for the hyperbola. It stretches it. All right, so big values of a, so bigger than 1, push it out at the corner, and values smaller than 1 make that corner a bit more square. So you can see all the way down to 0.01, it's where it's quite square, and then we gradually move our way further and further out, and the corner will round off. All right. Now, a couple of important features. As x gets bigger in either direction, so as it gets bigger negatively and bigger positively, the y value will get smaller and smaller. So it will approach 0, but as we knew from a hyperbola, it will approach 0 but never reach it. There is no way you can make that truncus touch the 0 when it hasn't been moved. All right. So as x gets towards 0, so as it goes from 1 inwards and -1 inwards, the y value actually gets bigger and bigger and bigger. And same as for a hyperbola, if you remember that, let's take a value of a half here. So a half squared, 1 divided by a half squared. So a half squared is 4. 1 divided by, sorry, a half squared is a quarter. A 1 divided by a quarter is 4. So that's actually, instead of x equals a quarter being here, it's now moved up to there. As the fraction gets smaller, when you square it, it becomes a bigger number, and therefore the y value is bigger again. All right, and the same thing happens in here. What the squaring does is that it removes the negative. All right, which is why in the first place the rectangular hyperbola lower left arm jumped over the x axis. So two things to keep in mind. As x gets bigger left or right, the y value gets smaller, and as x approaches 0 from the left or right, the y value gets bigger. All right, so that's having a look at the a value. We've just seen the dilation factor. I'll leave it as close to 1 as I can get, and we'll have a look at the h and k value. So again, h moves the thing sideways, and k moves the thing up and down. All right, so again, we have vertical and horizontal asymptotes. The vertical one is at x equals h. So if I put x at -3, the vertical asymptote is here. Even though there's been horizontal translation, the vertical asymptote is the one that's moved. And if I move the equation vertically, you can see that the bottom of the graph is moving, and therefore the horizontal asymptote is the one that's moving. All right. So, oops, I'll show you what I can do. If I enter another line here and say x equals h, we have there the vertical asymptote. So I'll select it, I'll change it to a dashed line because that's how we graph asymptotes. And then when I move my graph left or right, you can see the vertical asymptote moves with it. All right, I can do the same thing for a horizontal asymptote, y equals k. And again, I will change it to a dashed line. That's how we show asymptotes. And then when I move the truncus up and down, the horizontal asymptotes move too. All right. So the last thing I wanted to show you, I'll turn off those, is just a simple reflection. All right. So this graph you can see down the bottom here is one that's been reflected over the x-axis. It has exactly the same points as the original graph. It's just been reflected down. So this arm here has moved down, and this arm here has moved down there. All right. So these are all the transformations that can happen on a truncus. All right. There's the same horizontal translation as we already knew. There's the same vertical translation as we already knew, and there's the same dilation and reflection possible. All right. In the next video, we'll look at how to graph a few of them, but it's the same process as before. So if you want to skip that one, feel free to. All right, so a quick question. We need to sketch the truncus as shown here. Y equals -1 over 2 bracket x plus 3 squared minus 4. Now this one's a bit of a complex one to jump straight into, but the same process holds true as for every other graph. To sketch it, you need to know where the asymptotes are. You need to know where the x-intercepts are. You need to know where the y-intercepts are, and you need to know any other points. So let's just go one at a time. Asymptote. So we have a vertical asymptote, which is at x equals -3, which is the same as the horizontal translation. We have a horizontal asymptote at y equals -4, which is the same as the vertical translation. X-intercept we'll have to calculate, y-intercept we'll have to calculate, and any other points we don't need to know. But we do need to take care of this. This is a negative, which means it has been reflected. So we're going to expect to see the truncus here. All right, so keep that in mind. All right, we're going to expect to see it in those two quadrants. So first of all, let's find the x-intercepts. Now the x-intercepts are found by setting y equal to 0. So -1 over 2 bracket x plus 3 squared minus 4. Move the 4 across first as a positive, not a negative. -1 over 2 bracket x plus 3 squared. Multiply the denominator over to the left-hand side, sorry. So it should be 2 bracket x plus 3 squared bracket 4 equals minus 1. Divide everything that's not part of the x back, so it's going to be x plus 3 squared equals minus 1 over 8. I'll just make this a bit smaller to have some more room. Square root both sides, so it's going to be x plus 3 equals, square root both sides, so you're going to have x plus 3 equals the square root of minus 1 over 8. And at this point, if you just suddenly said, hold on a second, how do you square root a negative? Then we're on the right path. So let's go back and have a quick look at our transformations. We know it's been moved 3 units left because the x plus 3 shows us that. So 3 units, so there's our vertical asymptote. We know it's been moved 4 units down, so horizontal asymptote should be here somewhere. Now, going back to the original, we expected it to be somewhere like this. So question, is that going to cross the x-axis? No, and this step here has confirmed that we can't actually square root a negative number, so therefore we have to stop here, which shows us that there is no x-intercept. So we've not been able to find an x-intercept. Let's see if we can find a y-intercept. We should be able to see one if our quick sketch was anything to go by. So y equals minus 1 over 2 bracket 0 plus 3 squared minus 4. Y equals minus 1 over 2 bracket 3 squared minus 4. Y equals minus 1 over 18 minus 4. Y equals, all right, so this is going to be minus 4 and 1/18, which if you needed to know it in a improper fraction, which I like working with, you need to multiply 4 times 18 and then add 1, so it's going to be minus 73 over 18, which is a very big number to work with, big fraction to work with. So I've just extended our axis so we have room, and then, so we've got intercept there, we've got asymptotes there, we know it's been reflected, so we just have to graph it, and it's going to look something like this, with arrows on the end, and the other side is going to be there. Hopefully the left hand side looks something like the right hand side, but you'll notice again, like the hyperbola, that we don't actually graph very much of this side because of the transformations that have happened. That's entirely okay. You've just got to make sure that you put on the points you have got. So our last step is to label this. I won't label it as a coordinate, I'll just label it as minus 73 over 18. And the final thing to do is I like to write the equation of the truncus that we've graphed. All right, so to recap, same for hyperbolas, you need to know the information, which is asymptotes, x-intercepts, y-intercepts, and any other points you can find. Now, keep in mind, x-intercepts or y-intercepts, there may or may not be one or both of them, so you have to keep that in mind as you go through your solving. And when you hit a point, so long as you're confident you've done all the steps right, if you hit a point where it doesn't work, that shows you that you won't have that x-intercept or y-intercept. At the very beginning of the question, it's also helpful to do a quick sketch of where you think it might be to back up this problem that you run into. All right, so hopefully that makes sense. Let me know.